So if you go to the hospital with a broken arm, right, the medical X-ray you get it's incredibly binary.
Oh, yeah, totally.
It's like this masterpiece of visual precision. You hold up the film, the doctor points to a jagged white line on your radius, and that's it.
Right.
Broken or not broken, it's clean, it's definitive, and it leaves, well, very little room for interpretation.
Which is nice.
Yeah, it is. But when you step into a modern cockpit, specifically when you start looking at the legal and regulatory framework that governs the
Oh,
skies,
boy. Here we go.
yeah, you realize that the X-ray of aviation is this massive, invisible, constantly shifting web. It's not just one jagged line.
No, not at all.
It is thousands of overlapping international treaties and regional laws and highly specific operational tolerances.
Right, right.
And if you are what we call the learner, right, someone currently grinding through those late nights preparing to conquer the ATPL instrument exam.
The dreaded subject 010.
Exactly. Subject 010, air law. That web can feel like a brick wall of pure, unadulterated rote memorization.
It really can.
Yeah.
Which is exactly why we need to change how we look at it.
Mm-hmm.
Because if you treat air law as just, I don't know, a phone book of rules, you have to memorize for a 44-question, 2-hour exam.
Where 75% is the magic pass mark, by the way.
Right, exactly. If you just memorize it, you are going to be miserable.
Yeah.
And more importantly, the knowledge just won't stick.
Yeah.
Every single rule in this syllabus,
Yeah.
from the color of a taxiway light to the exact number of minutes you wait when your radio dies.
Right.
It exists because someone, somewhere, figured out the hard way that it needed to be there.
Yeah, written in blood, basically.
Yeah, we're looking at the foundational source code that allows, millions of people to be propelled through a three-dimensional, deeply hostile environment in aluminum tubes.
Yeah.
And somehow make it a routine, incredibly safe experience.
Which is wild when you actually think about it, and that is exactly the mission for this deep dive.
Yeah.
Whether you are prepping for the exam or you're, a seasoned commercial pilot refreshing your knowledge, we are going to decode that source code today.
Definitely.
We are pulling from a massive stack of EACE regulatory frameworks, comprehensive air loss study notes, theoretical knowledge learning objectives, and critically, the brand new ATPL syllabus updates.
The ECQB 2026 changes, those are huge.
Yeah, 2026 changes. So rather than just reading a list of bullet points, which is boring, we are going to build a hypothetical flight.
I like that.
We'll take an aircraft from the planning room onto the ramp, into the air, through a crisis, and back down to the runway, using the laws to guide us.
A chronological approach makes the most sense. Because before our hypothetical pilot even touches a flight planning computer, they're operating within a framework that was built long before they were born.
Right.
Understanding who writes the rules and why they have the authority to do so is the bedrock of Subject 010.
So let's wind the clock back. The sources point us to a very specific pivotal moment in history, which is the Chicago Convention in 1944.
Yeah.
Which, when you think about it, is an absolutely wild time to be holding a conference about civil aviation.
Right in the middle of it all.
Yeah. The Second World War isn't even over yet. The world is still in absolute turmoil. But you have delegates from 54 nations gathering in Chicago.
They must have been looking at all these massive military bomber fleets and just realizing that the moment the war ended, those assembly lines were going to pivot to civilian airliners.
The sky was about to explode with traffic.
Exactly. They possessed incredible foresight. They knew that if every single sovereign nation developed its own completely independent set of aviation rules, international air travel would be, well, it would be impossible.
Yeah, it would be chaos.
Imagine a pilot flying from New York to London to Paris. If the altimeter settings, the radio frequencies, the runway markings, and the licensing requirements changed fundamentally every time they crossed a border,
You'd crash.
the system would collapse. Out of that urgent realization in Chicago came the International Civil Aviation Organization, or ICAO. So ICAO is essentially the United Nations of Aviation.
Basically, yeah.
They sit at the top and set the global standards. And to do this, they produced a series of annexes. Now, there are 19 of them in total, but our study notes highlight the big 6 that are absolutely critical for the ATPL exam.
Right.
So if I'm piecing this together logically, before we can have rules of the sky, we need to know who's actually qualified to be up there. So that brings us to Annex 1.
Precisely. Annex 1 is personnel licensing.
Yeah, okay.
It establishes the baseline medical and training standards for pilots, air traffic controllers, and maintenance engineers.
Makes sense.
Once you have licensed personnel, you need to tell them how to interact with each other in the sky. That is Annex 2, the rules of the air.
So think of this as the basic highway code,
Right,
like who
right.
yields to who, how to overtake, the fundamental rights of way.
Right.
Okay, so we have the pilot and we have the highway code. But commercial aviation's a business. So Annex 6 steps in, covering the operation of aircraft.
Yeah, this dictates the procedures for flying as a commercial operator. Things like fuel requirements, dispatch procedures, company manuals.
And we can't forget the machine itself, right? Annex 8 is airworthiness.
Yes.
This defines the minimum standards to certify that an aircraft design is structurally sound and safe to fly.
And then once that airworthy machine is flying under commercial rules, it needs a system to guide it through congested airspace. That brings us to Annex 11, Air Traffic Services.
Okay, so ATC.
Yeah, ATC, Flight Information Services and Alerting Services.
Which leaves the darkest, but honestly, arguably the most important one for safety evolution. Annex 13, Accident and Incident Investigation.
This one is fascinating.
It is. What fascinates me here isn't just that they have rules for investigating a crash, but the explicit legal philosophy behind it. The core principle of an Annex 13 investigation is strictly to prevent future accidents.
Right.
It is not there to apportion blame or legal liability.
That distinction is crucial.
Right.
Highly testable on the exam. In most legal structures, an investigation is designed to figure out who is at fault so they can be sued or prosecuted.
Sure, like a car crash.
Right. But ICAO realized early on that if pilots and operators feared they would be thrown in jail for making an honest mistake, they would hide evidence.
Oh, absolutely. They'd cover it up.
They would lie. So a purely safety-driven, non-punitive framework encourages total transparency. We learn from the disaster so it never happens again.
So ICAO puts out these rules, and they divide them into two categories called SARPs, standards and recommended practices.
Yes, the wording here is very specific.
Yeah, the language is key. A standard uses the word shall, meaning it is mandatory.
Right.
A recommended practice uses the word should, meaning it's highly desirable but not legally binding. But going back to my UN analogy, the United Nations doesn't have a global police force.
No, they don't.
So if a sovereign nation looks at an ICAO standard and says, well, we actually can't do that here, what happens? Do they just get kicked out of the sky?
They don't. The brilliance of the Chicago Convention is that it relies on transparency as a safety net.
Okay.
If a state cannot or will not comply with an ICAO standard, perhaps due to their, mountainous geography or a lack of technological infrastructure, they are legally obligated to use a mechanism called filing a difference.
Ah, filing a difference.
Yes, they must officially notify ICAO, essentially saying, we do this specific procedure differently in our airspace.
And that gets published in their local aeronautical information publication, their AIP.
Exactly.
So our hypothetical pilot reading the charts knows exactly what curveballs to expect before they even start the engine. Standardization is the goal, but transparency is the fallback.
Perfectly said. Now, to bridge the gap between global standards and local law, we have regional authorities.
Yeah.
For Europe, that is ESA.
The European Union Aviation Safety Agency.
Right. ESA takes those ICAO annexes and translates them into hard enforceable regional law for its 31 member states.
So Annex 1, the personnel licensing, becomes ESA's Part FCL, flight crew licensing, and Part MMed for medical.
Yes.
Annex 6, operation of aircraft, becomes Part OPS. So EALESA is the entity actually handing out the fines and suspending the licenses if you break the rules.
That is the complete architectural foundation. The laws are written.
Yeah.
Now, let's put our pilot to work.
Yeah.
We are on the ground in the briefing room. Before we can legally occupy a slice of airspace, we have to formally request it.
Time to unpack the paperwork? The flight plan, or FPL?
The dreaded FPL.
Yeah, it is essentially a contract between the pilot and air traffic control. Our pilot sits down at the computer, and the first thing they have to declare is the rule system they are flying under.
Right.
There are 4 main types of flight plans. I is pretty obvious, purely instrument flight rules, IFR, for the entire journey. V is equally obvious, visual flight rules, VFR.
But modern commercial aviation often blends the two, especially when operating out of smaller, uncontrolled airfields before joining the high-altitude commercial airways.
This is where those mixed flight plans come in. You have Y, which means starting under IFR and then canceling it to proceed under VFR. The memory aid I used for this during my own studies was IVY. IFR to VFR is Y.
Oh, that's good.
And then there is Z, which is starting VFR and picking up an IFR clearance later in the flight. I remember that as VIZ. VFR to IFR is Z. IVY, and VIZ. It's an absolute lifesaver for multiple choice questions.
It is a great mnemonic. You'll definitely want to use that. Now, submitting that flight plan isn't something you can do as you are taxiing to the runway.
No.
The entire European airspace network, managed by Eurocontrol, relies on highly sophisticated computer algorithms to predict traffic flow and avoid bottlenecks hours in advance.
Right.
Therefore, the exam tests you heavily on submission timings, which are all based on EOBT.
The estimated off-block time.
Yes, that is the moment the aircraft first moves under its own power.
So let me see if I can logic this out. If I am flying in completely uncontrolled airspace, ATC isn't providing separation services between me and other aircraft.
Right, you're on your own mostly.
I'm mostly just giving them my plan for search and rescue purposes, so they don't need massive advance warning. The rule says uncontrolled airspace requires the FPL to be filed at least 30 minutes before EOBT.
That's the sound logic. Now apply it to controlled airspace.
Okay, if I'm flying into controlled airspace, ATC is now legally responsible for keeping me separated from everyone else.
Exactly.
Their computers need time to ingest my route, calculate my climb profile, and sequence me into the flow, so they demand more time. The FPL must be filed at least 60 minutes before EOBT.
Spot on. And what if our pilot takes off VFR from a grassy farm strip, perfectly legally without a flight plan, but halfway through the flight realizes the weather is deteriorating ahead and they need to cross a controlled airspace boundary?
The airborne filing rule.
Yes.
They must submit the plan over the radio at least 10 minutes before reaching that controlled boundary, which, honestly, at commercial cruising speeds isn't very far away, so they'd better be talking fast.
They really do. But aviation's dynamic. Delays happen, the passengers are late, the catering truck breaks down.
Always the catering truck.
Always. The exam will test you on refiling timings. Basically, how long your original flight plan remains valid in the computer before ATC deletes it and you have to start over.
Right.
If you are operating in uncontrolled airspace, you have a generous buffer of EOBT plus 60 minutes.
But if you're heading into controlled airspace, that tightly wound algorithm can't just keep a ghost slot open for you forever while you wait for the catering truck.
No, it would ruin the flow.
So the buffer shrinks. You only have EOBT plus 30 minutes before you must submit a delay message or refile.
Now, let's look at what happens when our pilot actually gets airborne. The plan is active. But suddenly, they catch a massive jet stream tailwind. Or perhaps ATC gives them a massive shortcut, a direct routing that shaves miles off the flight.
Okay.
The pilot knows things have changed, but when do they legally have to tell ATC?
This one is crazy to me. The tolerances in the syllabus are shockingly tight.
They are.
You must notify ATC if your true airspeed, your TAS, varies by plus or minus 5% from what you filed. Or, and this is the one that blows my mind, if your estimated time of arrival, your ETA, at the next reporting point changes by more than 2 minutes.
2 minutes.
2 minutes. If I'm driving to meet a friend and I'm 2 minutes late, I don't even send a text. Why is ATC so obsessed with 120 seconds?
Well, put yourself in the shoes of an approach controller at, say, Frankfurt or Heathrow.
Okay.
You are staring at a radar screen with 40 heavy jets converging on a single piece of concrete. Your sequencing is based entirely on the speeds and times those aircraft told you they would achieve.
Right.
You have engineered it so that aircraft A crosses a waypoint exactly 3 miles ahead of aircraft B. If aircraft A suddenly slows down by 5% or arrives 2 minutes late, they are now occupying the exact block of sky that aircraft B was supposed to slide into.
Oh, wow.
The entire arrival corridor dominoes.
Wow.
2 minutes at 500 knots is over 15 miles of distance.
That's huge.
That is the difference between a safe landing and a mid-air collision.
Okay, when you visualize 15 miles of distance, 2 minutes suddenly feels like an eternity.
Yeah.
Now, what if the pilot has a passenger with a medical emergency and they have to completely abandon the plan and divert to a different airport?
The primary rule here is to notify the original destination aerodrome within 30 minutes of the diversion.
30 minutes?
Right. If the destination airport expects you at 14.00 and 14.30 rolls around with no sign of you and no communication, they are legally required to trigger search and rescue protocols. I don't want helicopters launching to look for your wreckage just because you forgot to make a phone call after diverting for a sick passenger.
Yeah, that would be a bad day. So there are a couple of administrative loose ends to tie up before we push back from the gate.
Oh.
If a major airline flies the exact same route from London to Geneva every single morning at 7 a.m., surely their dispatchers aren't manually typing in the same waypoints every single day?
No, they utilize repetitive flight plans. If a specific flight operates on the same days of consecutive winks on at least 10 occasions, or if it operates every single day over a 10-day period, the operator can file a repetitive plan.
So it just stays in the system?
Exactly. It stays in the system and just activates automatically. It drastically reduces the administrative burden on both the airline and Eurocontrol.
The final piece of pre-flight prep is knowing if the aircraft actually fits at the airport. This is governed by the Aerodrome Reference Code.
Right.
It's a two-element code that defines the physical dimensions an airport can handle. Element 1 is a number based on the reference field length, essentially how much runway is available. A1 means less than 800 meters. 2 is 800 to less than 1,200 meters. 3 is 1,200 to less than 1,800 meters. And 4 is anything 1,800 meters or greater.
And element 2 is a letter from A through F representing the aircraft's wingspan and outer main gear span. So if you see an airport charted as code 4F, you immediately know it has a runway over 1,800 meters long and taxiways wide enough to accommodate the massive wingspan of an Airbus A380 or a Boeing 747-8.
Awesome. All right, so our pilot has filed the paperwork, checked the aerodrome codes, and we are finally taking off. We're climbing into the cruising altitudes. The most pressing legal question now is, how do we share this invisible three-dimensional volume of air safely without hitting anyone?
Right, because there are no lanes painted on the clouds.
Exactly.
The most elegant solution to preventing mid-air collisions in cruising flight is the semicircular flight level rule. It dictates your vertical altitude based entirely on your magnetic track across the Earth.
It's beautifully simple for IFR flights. If our pilot is flying westbound, meaning a magnetic track anywhere from 180 degrees through to 359 degrees, they are assigned an even flight level.
Like flight level 300, 320, 340.
Right. If they turn around and fly eastbound 1,000 degrees through to 179 degrees, they must fly at an odd flight level 310, 330.
Evens west, odds east.
Evens west, odds east. It applies all the way up to flight level 410. Just by looking at your compass, you know which slice of the sky belongs to you.
It works perfectly for aircraft flying on instruments under ATC control. But the sky is also full of visual flight rules, or VFR, traffic smaller aircraft flying by looking out the window, often without talking to radar controllers.
Yeah.
VFR traffic follows the same fundamental east-west split, but the law requires them to add 500 feet to the altitude.
Right.
So a westbound VFR flight wouldn't be at flight level 80. They would fly at even plus 500, making it flight level 85. Eastbound VFR is odd plus 500, like flight level 95.
I always wondered about the specific geometry of this when I was studying. Why 500 feet? Why not just put them all at the same altitudes but make VFR planes keep a sharper lookout?
Let's visualize the airspace as a layer cake.
Okay, layer cake.
IFR aircraft are separated vertically from other IFR aircraft by 1,000 feet. So you have a heavy jet at 10,000 feet and another one at 11,000 feet. The space in between is empty. By forcing VFR traffic to fly exactly in the middle, at the 500-foot mark, say 10,500 feet, you maximize the vertical distance between everyone.
Oh, I see.
If an IFR plane is climbing through a thick cloud layer, completely blind to the outside world, the absolute worst place for a VFR Cessna to be is skimming the very top of that cloud at the exact same altitude.
Yeah, that's a collision waiting to happen.
The 500-foot offset guarantees that when the IFR jet punches out of the top of the cloud, the VFR traffic is a full 500 feet above them. It mathematically guarantees half 1,000 feet of separation between rule types.
That layer cake visual is brilliant. It makes the rote numbers mean something. Now, what about the bottom of the cake? How low are we legally allowed to go? The rules for minimum flight levels under IFR.
The absolute golden rule, overriding everything else, is that you never fly below the state-published minimum altitude.
Obviously.
But as a baseline, in normal, flat, or rolling terrain, an IFR flight must remain at least 1,000 feet above the highest obstacle within 8 kilometers of the aircraft.
I'm assuming that buffer has to change if you are flying over, like the Alps or the Rockies.
The double sobels, wow.
Yes. The altimeter in an aircraft relies on air pressure, and high winds blowing over jagged mountain peaks can create localized low-pressure zones that make your altimeter overread. It might tell you that you are at 10,000 feet, but you are actually at 9,000.
That is terrifying.
It is. To account for this invisible aerodynamic trap, mountainous terrain requires an IFR aircraft to be a full 2,000 feet above the highest obstacle within 8 kilometers.
What if our pilot cancels their IFR plan and decides to fly down low under VFR? The low-flying rules shift dramatically. Over-congested areas, cities, towns, open-air assemblies of people VFR cannot fly lower than 1,000 feet above the highest obstacle within 600 meters of the aircraft.
Right.
Over non-congested areas, the absolute hard deck is 500 feet above the ground or water, except when legitimately taking off or landing. And since we are discussing visual flight rules, we have to talk about the weather requirements that make them legal. VMC minima, or visual meteorological conditions.
Right.
If you want to fly VFR in controlled airspace near an airport, an aerodrome traffic zone, an ATZ, or a control zone, a CTR, the law requires a baseline of a 1,500-foot cloud ceiling and 5 kilometers of forward visibility.
But weather isn't always cooperative. If the visibility drops to 4 kilometers, is our VFR pilot just stuck on the ground?
Not necessarily. They can request special VFR, or SVFR, from air traffic control.
Ah, okay.
This clearance allows a reduction in the legal visibility requirement all the way down to 1,500 meters. However, there's a massive trap here for the exam candidate.
A trap.
Yes. Special VFR is a service provided only within a control zone, a CTR. A CTR is a specific block of controlled airspace protecting an airport. If you are at a small airfield that only has an ATZ, an aerodrome traffic zone, which is not embedded inside a larger CTR, you legally cannot get a special VFR clearance.
Oh, wow.
The service literally does not exist there.
That is exactly the kind of nuance they will use to catch you out on a multiple choice question. SVFR equals CTR only.
Yep, burn that into your memory.
Okay, let's look quickly at our interactions with ATC radar while we are cruising along. If a controller says they have lost our radar tag and asks us to execute an identification turn so their computer can track our primary radar return, how far do we have to turn?
The syllabus requires a heading change of 30 degrees or more.
30 degrees.
Yes. If you only turn 10 degrees, the radar software might interpret that as the aircraft simply crabbing sideways to correct for a wind gust, and it won't trigger the identification protocol.
And when we first take off, we are legally considered identified on primary surveillance radar once we are 1 nautical mile past the departure end of the runway.
Exactly.
Now, our transponder is also constantly broadcasting our altitude to ATC utilizing Mode C. How accurate does that broadcast have to be legally?
In standard, non-RVSM airspace, the tolerance is plus or minus 300 feet. But if you are flying high up in the flight levels, typically above flight level 290, you enter RVSM airspace.
Reduced vertical separation minimum.
Right. Up there, the tolerance tightens significantly to plus or minus 200 feet.
I can deduce why. In RVSM airspace, the vertical separation between opposing traffic is squeezed from 2,000 feet down to just 1,000 feet to pack more planes into the sky.
Exactly.
If your altimeter is off by 300 feet and the guy above you is off by 300 feet in the other direction, that 1,000-foot safety buffer suddenly shrinks to just 400 feet.
And that's too close for comfort.
Yeah. The equipment simply has to be twice as accurate to justify the reduced separation.
The margins for error just disappear.
Okay, perfect separation is beautiful when everything is working. The algorithms are humming, the transponders are pinging, everyone is in their correct layer of the cake.
Right.
But aviation is defined by how we handle the moments when the systems fail. What happens when the radios go completely silent? Or worse, when there is a fire on board. This brings us to a massive, critical part of our deep dive. Emergency procedures and the highly anticipated 2026 ECQB syllabus updates.
Oh, this is the section where every learner listening needs to sit up and take notes because the laws here are actively changing beneath our feet.
Yeah, pay attention to this part.
But let's begin with the constants, right? How we categorize and declare an emergency. Air law divides emergencies into 2 strict tiers: distress and urgency.
Distress is the ultimate nightmare scenario. It is legally defined as being threatened by grave and imminent danger, requiring immediate assistance.
Immediate is the key word.
On the radio or over a data link, the distress signal is the word we all know. Mayday, mayday, mayday. If your radios are dead and you are relying on visual signals, distress is indicated by firing a parachute flare showing a red light, or by taking a red light and throwing it from the aircraft at regular intervals.
The operational keyword there is immediate assistance. The situation is critical right now. The second tier is urgency.
Okay.
This is a condition concerning the safety of an aircraft or someone on board, which compels a landing, but where immediate assistance is not required. You have a problem, You need priority handling, but you aren't falling out of the sky.
So for an urgency situation, the radio call is pan, 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 pan. Or if you are using Morse code or data link, it's the letters XXX.
Correct.
Visually, an aircraft can signal urgency to the tower or to another aircraft by repeatedly switching their landing lights on and off or toggling their navigation lights on and off.
But what happens if the emergency isn't an engine failure or a fire? What if the emergency is simply that your communication radios have completely died? You are perfectly safe, the engines are running, but you are a ghost in the system?
If our pilot is flying in VMC visual meteorological conditions, where they can see the ground and other aircraft can see them, the rule is wonderfully simple. The law says, continue your flight in VMC, land at the nearest suitable aerodrome, and report your arrival to ATC by the most expeditious route, which basically translates to land the plane, find a telephone, and call the approach controller to tell them you are safe.
That is the easy scenario.
Yeah.
The nightmare scenario is experiencing a total communications failure while deeply embedded in IMC instrument meteorological conditions.
Oh, man, in the clouds.
You are in the clouds, totally blind to the outside world, flying solely on instruments. For decades, the rules governing this exact scenario have been complex, based heavily on what type of airspace you are in. And this is exactly where the ECQB 2026 update has completely rewritten the playbook.
Let's unpack this carefully, because a mistake here on the exam is devastating.
It really is.
Under the old syllabus, the IMC comms failure rule depended on radar. If you were flying in a radar environment where ATC could see your blip and your radio died, you were legally required to maintain your current speed and altitude for exactly 7 minutes. If you were in a procedural environment, meaning out over the ocean or in a remote area with no radar coverage, you had to maintain for 20 minutes.
Yes.
After that waiting period, you were to proceed to the navigation aids serving your destination, hold there until your estimated approach time, and then shoot the approach, ideally landing within 30 minutes of your ETA.
That was the old rule. The fundamental earth-shattering update in the ECQB 2026 syllabus is that they have entirely abolished the 7-minute rule.
Abolished it.
Yes. They have extended the radar communications failure timing from 7 minutes to 20 minutes. Both radar and procedural environments now utilize a universal 20-minute maintain period.
Wait, I need to stop you there. Because there are thousands of learners who have printed study notes sitting on their desks right now that say 7 minutes.
I know.
But the new syllabus says 20 minutes. If I am walking into the examination center next week, which number do I click on the screen? This feels like a trap.
This is the most vital warning we can give on this deep dive. You absolutely must verify your approved training organization's transition timeline.
Okay.
The implementation of the 2026 syllabus is not a simultaneous global switch. It differs between EASA member states and national aviation authorities.
So it could be different depending on where you sit the exam.
Exactly. If your exam center is still pulling from the old question bank, the correct answer is 7 minutes. If they have transitioned to the 2026 bank, the answer is 20 minutes.
Wow.
You need to ask your chief ground instructor immediately. If your ATO is transitioned, throw your old notes in the bin.
But why did EASA make such a massive change anyway? Flying straight and level for 7 minutes with a dead radio feels like a long time. Flying for 20 minutes feels like an eternity. Why force the pilot to wait so long before starting their approach?
It is a direct reflection of how incredibly congested modern European airspace has become. Let's go back to our controller at Frankfurt.
Okay, the 40 jets.
They're managing 50 aircraft now. Suddenly, one aircraft loses its radio and stops responding. Under the old rule, after just 7 minutes, that ghost plane would suddenly turn and start executing a pre-planned lost comms procedure, descending and routing toward a holding fix.
Right.
7 minutes is not enough time for the controller to manually vector 49 other heavy jets out of the way.
Oh, I see.
By forcing the ghost plane to maintain its current heading and altitude for 20 minutes, the law gives ATC the time they desperately need to scramble. They can build a massive, protective, empty bubble of airspace around the lost comms aircraft's projected flight path.
Ensuring that when the plane finally does turn toward the airport, it won't hit a single thing.
Exactly.
That makes perfect sense. The rule isn't for the pilot. The rule is to give ATC time to clear the board.
Yes.
And speaking of giving ATC information, the 2026 syllabus introduces a brand new transponder squawk code. We know the classics. 7500 is hijack, 7600 is comms failure, 7700 is a general emergency. But now we have 7601.
Yes. 7601 is specifically engineered for an IFR aircraft that experiences a communication failure while operating in VMC.
Oh,
Previously, they would just squawk 7600, which told ATC, "I've lost my radios." But it didn't tell ATC if the pilot was in a cloud or in clear blue skies. Squawking 7601 gives ATC incredibly granular data. It tells the controller, "I have lost my radios, but I am in visual conditions and I am self-separating."
that is so smart. What else is lurking in the 2026 syllabus? Because looking at the source material, the exam seems to be dragging itself forcefully into the modern era.
The updates are vast. There's a completely new section focused entirely on U-Space.
U-Space.
Yes, this is the new regulatory framework designed to integrate uncrewed autonomous drones into European airspace alongside manned aircraft.
That is a massive paradigm shift. I want to circle back to that at the very end. What about weather and flight planning?
They have completely overhauled the meteorology section to incorporate the new WAFC T+24 CIGWX charts. For decades, pilots relied on black and white, highly cryptic, significant weather charts.
They were terrible to read.
Awful. The new standard introduces color, which vastly improves human factors readability. They feature updated annotations for enhanced icing and turbulence reporting. And notably, the syllabus introduces academic material regarding the impacts of climate change on aviation operations for the first time.
I also see significant changes to fuel management.
Yes, the academic theory is finally catching up to modern airline dispatch reality. The syllabus features new definitions and calculation methods for contingency fuel and discretionary fuel, focusing on energy management as a holistic concept rather than just counting gallons in a tank.
Nice.
And finally, there is a massive expansion on human performance, specifically fatigue risk management, or FRM.
Why sudden focus on fatigue?
Because the industry realized that simply telling a pilot, "You can legally fly for 8 hours and then you must sleep for 10 hours, doesn't actually prevent exhaustion.
No, especially with time zones.
Right. FRM shifts the focus to biomathematical fatigue models. It recognizes that circadian rhythms, crossing time zones, and consecutive early starts compound fatigue. Managing human rest is now treated with the exact same mathematical rigor as managing the fuel in the wings.
Okay, so the learner needs to be acutely aware of 2026. Let's move to the next phase of our hypothetical flight. Whether our pilot is dodging drones, managing a comms failure, or just flying a standard approach, eventually they have to find the runway.
Hopefully.
Let's talk about visual aids and aerodrome markings. If all the radios die, what is the ground trying to tell us visually?
The ultimate fallback system is the manual light gun signals from the control tower. If you are an aircraft in the air, a steady green light from the tower means cleared to land. A steady red light means give way to other aircraft and continue circling.
See the design language here. A steady light is an absolute definitive command. Steady green is land. Steady red is stay away. What about flashing lights?
Flashing lights are generally environmental instructions or commands to move somewhere else. A flashing green light to an airborne aircraft means return for landing. It is essentially a clearance to come back to the traffic pattern, but you still need a steady green to actually touch down.
Got it.
A flashing red light means aerodrome unsafe, do not land.
Yeah.
A flashing white light means land at this aerodrome and proceed to the apron.
And if the tower controller fires a literal red pyrotechnic flare into the sky?
That is the highest priority visual signal in existence.
I bet.
It means, notwithstanding any previous instructions, do not land for the time being. It overrides everything.
Let's apply that same design language to an aircraft that is on the ground, taxiing.
It translates perfectly. On the ground, a steady green absolute command means cleared for takeoff. Flashing green means cleared to taxi. Steady red absolute command means stop. Flashing red means taxi clear of the landing area in use. And a flashing white light means return to the starting point on the aerodrome.
Knowing those light gun signals is practically a guaranteed point on the exam.
Oh, absolutely.
Now, speaking of visual fallbacks, let's look at the signal square. This is usually a 3 by 3 meter square, outlined with a white border, located prominently on the airfield. Inside it, ground crews place large physical symbols. A large T shape means you must take off and land in a direction parallel to the shaft of the T towards the crossbar.
Right.
A cross shape means gliding operations are underway, and H means helicopters are active.
Then you have the dumbbell shapes.
Yeah.
A plain dumbbell symbol means you must keep the aircraft exclusively on paved surfaces. A dumbbell with black stripes across it means you must take off and land on the paved runway, but you are permitted to taxi on grass or unpaved areas.
Okay.
A red L placed over a dumbbell means light aircraft are permitted to use the runway or a specially designated area.
Then there are the squares. A red square with the single yellow diagonal line means care should be taken on maneuvering areas due to poor condition. A red square with a yellow cross means the aerodrome is completely unsafe and you absolutely cannot land.
Yeah.
Now, I have to be honest here. A dumbbell with a black stripe. I look at that symbol, and it literally looks like someone left gym equipment out on the grass.
It really does.
How is a pilot, bouncing around in turbulence at 1,000 feet, supposed to spot a single black stripe on a canvas dumbbell sitting inside a 3 by 3 meter square?
It's a very fair criticism. To understand the signal square, you have to understand its history.
Yeah.
It is a direct relic of the 1920s and 30s.
Oh, okay.
Back then, biplanes didn't have radios, and they flew much slower and much lower to the ground. A pilot in an open cockpit could easily lean over and read the canvas symbols on the grass.
But why is it still taking up space on a 2026 ATPL syllabus?
Because it represents the ultimate zero electricity safety fallback.
Ah.
If a massive solar flare knocks out every satellite, every radio tower, and the entire power grid of the airport, paint and canvas on the grass don't need electricity. As an aviator, you are tested on the signal square because you are expected to know how to navigate the absolute worst-case scenario.
Fair enough. Let's talk about the aids that do rely on electricity. Beacons and lighting. Our pilot is approaching the airport at night. How do they find it?
Aerodrome identification beacons flash a specific two-letter Morse code sequence. If it is a land aerodrome, the light flashes green Morse. If it is a water aerodrome, like a seaplane base, it flashes yellow Morse.
Right.
But general aerodrome beacons, which just rotate continuously to help you locate the airport from miles away, flash white or alternating white and green for a land airport and white or alternating white and yellow for a water aerodrome.
Okay, we've found the airport, we've landed. The taxiway edge lights guiding us to the gate are blue. But if the airport operates in low visibility procedures, LVPs, meaning heavy fog, they will activate green centerline lighting on the taxiways.
Yes.
We also have to watch out for alternating green and yellow lights. Those mark the critical or sensitive perimeter areas around the ILS antennas. We cannot stop the aircraft there, or our massive metal fuselage will warp the radio signal guiding other planes in to land.
And while we are still in the air looking at the runway itself, there is a specific lighting warning system. If a runway is intended for use in runway visual range, or RVR,
Right.
conditions of less than 400 meters, it must have red centerline lights installed for the final 300 meters of the pavement.
Oh, that makes sense.
When the pilot sees the centerline turn red in the fog, they know the concrete is about to end.
Let's talk about the paint on that concrete. Runway markings. Runways can range anywhere from 18 meters wide for small fields up to 60 meters wide for major international hubs. The syllabus states that the number of threshold stripes, the longitudinal piano keys painted at the very start of the runway, tells the pilot exactly how wide the runway is.
Right.
The math formula in the note says runway width equals 4 times the number of stripes.
Exactly. So instead of trying to memorize a formula, translate it into a visual. If our pilot breaks out of the clouds at 200 feet and sees 12 piano keys painted across the threshold, they can instantly do the math.
12 keys multiplied by 4 equals a 48-meter wide runway.
That is so much easier to process in a cockpit. What about the aiming point? Those two massive, thick white blocks painted down the runway that give the pilot a visual anchor to aim for.
Right.
The location of the aiming point changes based on the available landing distance. For a shorter runway, between 1,200 and 1,500 meters long, the aiming point is painted 300 meters down from the threshold.
Okay.
But if the runway is longer, between 1,500 and 2,400 meters, the aiming point gets pushed further back to 400 meters down the runway.
I can deduce why that is. A longer runway usually means larger, heavier aircraft are landing there.
Yes.
A Boeing 777 has a much higher approach speed and a flatter glide path than a Cessna. If the heavy jet aims too close to the threshold, its massive main landing gear might actually clip the approach lights before it even reaches the concrete. Pushing the aiming point 400 meters down the runway guarantees a safe crossing height over the threshold.
Precisely. The paint reflects the physics of the aircraft. To help pilots hit that aiming point, we use visual glide slope indicators.
Right, the lights next to the runway.
The TVASI system consists of 4 light units on each side of the runway, forming a wing bar, with 6 longitudinal lights bisecting it. The ATVASI is the abbreviated version. It's only installed on one side of the runway, but it still utilizes 4 light units.
Okay.
And crucially for the exam, all these visual systems, VSI, PAY-PI, are engineered to provide safe obstacle clearance for aircraft, whose pilot eye height over the threshold is between 12 meters and 16 meters.
If the airport is equipped with a SAC-2 or CAT-3 instrument landing system, the ultra-high-precision radio beams used for landing in zero visibility, the physical lighting on the runway gets a major upgrade to match.
Definitely.
They install a white centerline barrette and 2 red side barrettes starting exactly 300 meters from the threshold.
And finally, when the rubber meets the runway, our pilot needs to know how much grip they actually have. This requires knowing how to read runway skates and snow tams.
The snow reports.
Yes. The definitions are highly specific. A runway is legally damp if there is just a change of color on the surface due to moisture. It is wet if it is soaked but has no standing water.
Got it.
Water patches is self-explanatory. And flooded means there is extensive standing water, which introduces a massive risk of aquaplaning.
For winter operations, airports issue snow tams, which report the braking action on a scale from 1 to 5 based on physical friction tests.
You need to know this scale.
Yeah, a 1 is poor, meaning a friction coefficient of just 0.25. If you hit the brakes, nothing happens, you just slide. 2 is poor medium. 3 is medium, a coefficient of 0.30. 4 is medium good. 5 is good, meaning a coefficient of 0.40, which feels like braking on a normal wet road. And a 9 means the conditions are so rapidly changing that they are unreliable to measure.
That 1 to 5 scale is incredibly testable. You must know the corresponding friction coefficients.
All right, our hypothetical flight has safely navigated the rules, the emergencies, the lights, and the snowy runway. But before a pilot is ever allowed to do this for real, they have to prove their skills to an examiner.
The check rat.
Let's dive into instrument check ride tolerances and reporting. When you are flying under IFR and ATC asks for a position report, what legally has to be in that radio transmission?
A standard position report contains 3 strict items. First, your position where you are right now. Second, operational information, which means your ETA to the next waypoint and your remaining endurance, meaning your fuel on board.
Okay.
Third, meteorological information, but only if specifically required or if you encounter severe icing or turbulence.
Speaking of meteorology, ATC has strict legal triggers for when they must break into the radio chatter to report weather changes to an aircraft on final approach.
Yes, they do.
They are required to report runway visual range, RVR, the moment it falls below 1,500 meters. And for the wind, they have to notify the pilot if the mean headwind changes by 10 knots, if the mean crosswind changes by 5 knots, or if the mean tailwind changes by just 2 knots.
I want to highlight that last one. A 2-knot tailwind change sounds completely insignificant, the gentle breeze.
Right.
But you have to understand the physics of a swept-wing heavy jet. If you are calculating your landing distance on a wet runway at maximum landing weight, a mere 2-knot increase in your tailwind can exponentially increase the runway distance required to stop.
Oh, wow.
It can be the literal difference between stopping safely on the pavement and sliding off the end into the grass. That's why the reporting tolerance is so incredibly tight.
So when the examiner is sitting next to you on your ATPL check ride, evaluating all of this, what are the flight tolerances?
The overarching legal standard for passing a check ride is that the successful outcome of a procedure must never seriously be in doubt.
That sounds slightly subjective. How do they quantify never in doubt?
They quantify it with hard numbers. Practically, it means maintaining your assigned altitude within plus or minus 100 feet. Your tracking on radio navigation aids must be within plus or minus 10 degrees of the center line. If you are flying a modern RNAV approach using a GPS displaying range and bearing to a point, your cross-track error must remain within plus or minus 2 nautical miles to 3 nautical miles, depending on the phase of the flight.
And for the basic hand-flying maneuvers?
In straight and level flight, you must hold your assigned heading within plus or minus 10 degrees and your indicated airspeed within plus or minus 10 knots. If the examiner asks for a turn, your bank angle must remain within plus or minus 15 degrees and your speed within 10 knots.
Right.
Small deviations in your rate of turn are permitted up to half or full scale on the turn coordinator, as long as your airspeed remains locked within a 15-knot window.
There is one highly specific note in the source material regarding the simulators used for training an instrument rating instructor outside of an approved training organization. The law states the primary flight controls must be instantly accessible to both the student and the instructor, and it explicitly mandates swing-over flight controls should not be used. A swing-over yoke is a single steering wheel that you can physically flip from the left seat over to the right seat. Why is that specifically banned for instrument instruction?
It ties directly back to that standard of the outcome never seriously being in doubt. When an instructor is teaching a student to fly solely by reference to instruments, spatial disorientation can occur in a fraction of a second.
Right, the leans.
Exactly. The student's brain tricks them into thinking they're flying straight when they're actually in a diving bank. If they aggressively put the aircraft into an unusual attitude, the instructor must take control immediately.
Okay.
If the instructor has a swing over yokes, they have to unlatch it, swing it over the center console, and lock it into their side before they can input a correction. That physical delay is maybe 2 or 3 seconds.
Which is an eternity.
But in hard IMC, close to the ground, 2 seconds of uncontrolled diving is the mathematical difference between a successful recovery and a fatal accident. The instructor requires instantaneous, hard-linked intervention capability.
See, when you explain the structural safety requirement behind the rule, it stops being a random bullet point to memorize. It becomes a vivid, life-saving mechanism.
Precisely. And that is the secret to mastering air law. Every single rule is written in the context of safety first, usually paid for by the lessons of the past.
Which brings us to the end of our hypothetical flight and the end of our deep dive. We have covered a massive amount of ground today, from the diplomatic foresight of the 1944 Chicago Convention down to the geometric brilliance of the 500-foot VFR offset and the exact friction coefficient of a snowy runway. The ATPL Air Law exam is undeniably a grueling test of precise memory and interpretation.
It is.
To the learner listening, do not just memorize the lists, understand the algorithms of airspace capacity, visualize the layer cake of altitude rules, and utilize mock exams to track your readiness. And most importantly, double-check your ATO's timeline for the 2026 ECQB implementation. You do not want to be the candidate who gets caught between a 7-minute and a 20-minute comms failure rule on exam day.
Absolutely. The transition periods are historically where the most candidates get caught out. Ask the question, verify the bank, study the rules that apply to the exact software version you will be tested on.
Now, I want to leave everyone with a final provocative thought. Building on something you mentioned earlier, the 2026 syllabus places a massive new emphasis on U-Space, the legal and technical framework for integrating uncrewed autonomous drones into European airspace alongside passenger jets.
Yeah, U-Space?
It is a huge, necessary step forward for the industry, but it raises an incredible question about the future of air law. As our skies fill with these autonomous machines, how will our legacy rules evolve? We just spent time discussing visual signal squares with canvas dumbbells, red parachute flares, and manual light gun signals from a control tower.
Right.
When the pilot in command of an aircraft is actually a sophisticated AI algorithm running in a server farm thousands of miles away, completely devoid of human eyes, does a flashing red light from a tower still mean anything? How do you signal urgency to a machine? It's something to think about the next time you look up at the sky.